Hey there folks, In the last video, I delidded an Intel 14700K by lopping the IHS off at the wrist, and then installed an Iceman direct die water block with liquid metal. Next, I turned my attention to an NVIDIA RTX 4090 that could have truffle shuffled with its gigantic OEM midsection. We replaced that with a svelte full-cover nickel water block that, with some luck, will enable 480p gaming at a solid 30 frames per second while staying cool as a cucumber under load. In this video, I'm going to finish the reinforcement of the frame backplate, add the carry handles to the frame, install the reservoir pump combo, and finally route the hardline water tubing between the components. I'm not sure what we're about to see, but I assure you, this B-movie is filled with A ideas. My first goal is crafting some handlebars to increase the frame's mobility. I'll cut two sections of aluminum that measure 17 3/4 inches long, lay them both out on the table, and put marks on both lengths at 6 7/16 inches, 7 5/8 inches, 10 3/16 inches, and 11 3/8 inches. Then I'll use a 1/4 inch center punch and hammer to place a pilot divot at each of these locations. Next, I'll move over to the drill press, where I've inserted a 7/32 drill bit, and will drive all the way through the aluminum at the 4 marks. I'm reusing the handles that were taken off the Chenbro case from episode 2, but I want to improve them a little bit. The hand grip attaches to the support plate via two 1/4x20 countersunk bolts. I want to make sure these two screws don't wobble, come loose, or need tightening over time. I'll wrap a shop towel around the handle grip and secure it in the tabletop vise. To permanently secure these screws, I'm going to use 271 red thread locker. Though I should note, I am not going to prime the threads, but rather just going to use straight thread locker. Using a Phillips screwdriver, I'll remove the first screw and generously apply thread locker to the bolt. Then I'll position it back in the hole and tighten down as far and as tight as it will go. Then I'll repeat these steps for the screw on the other side of the handle. After both sides are complete, I'll take the handle out of the vise, set it to the side, and repeat these steps for the two screws on the other handle. Once both handles have been doctored up, I'll let them cure for 18 to 24 hours, or until I get impatient. Okay, it's been about 20 minutes and I'm ready to prepare the handlebars. The hardware I'll use to attach the handles to the bars are 1 1/4 inch number 1024 combination head screws, washers with a 3/4 inch outer diameter and a 3/16 inch inner diameter, and 1024 nylon lock nuts. I'll use a trigger clamp to secure one of the bars to the table, and then lay the handle over the bar and align the 4 front holes on the handle with the holes that were drilled in the bar. With the holes aligned, I'll drop a 1024 screw into each, and then from the bottom, I'll add the washer, and then lightly thread the nylon lock nut onto each screw. Once all 4 screws have been started, I'll use a Pittsburgh mini ratchet and socket to tighten the lock nuts down completely, while using the screwdriver to provide stable tension so the screws don't move during the process. As I tighten each screw, I'm making sure to continually push the handle toward the screws, so that it is seated as far forward as possible. One handlebar completed, one more to go. I'll set this handle to the side and repeat these steps to attach the other handle to the other bar. The aluminum bars and steel handles are very strong as is, but I'm going to add additional reinforcement to each handle where there isn't metal-to-metal contact. I'll cut 4 lengths of aluminum that are 1 1/8 inches long. Before I can attach these posts, I need to enlarge these 2 holes on each handle to accommodate the M5 screws I'll use to attach them. For this, I'll put a 7/32 bit in the drill, bore each hole to be slightly larger, and then use needle files to gently shave down any ridges that may have formed. With all 4 holes drilled, I'll roll a T-nut onto a post, and then insert a leg of an interior corner bracket in the channel that faces 90 degrees away from the slot with the T-nut in it. Then I'll insert the other leg of the interior corner bracket into the handlebar slot backwards, and slide the post into position under the handle edge. Once it's in the general position, I'll turn the handle around and nudge it into place until the hole on the handle aligns with the T-nut in the slot. Now I'll use a hex wrench to tighten the 2 set screws for the interior corner bracket, and then insert an M5 8mm screw through the hole on the front and tighten down completely. I'll repeat these steps to add the second post to the handle. Once the second post is added, the handle now looks like this. I'll repeat these steps again to add the 2 posts onto the second handlebar. Both handlebars are now complete and ready to be added to the frame. On the back of the frame, I'll use a scrap piece of aluminum as a stop block between the handlebar and the vertical support. Then I'll use a mini bar clamp on the bottom of the handlebar to temporarily secure it into place. On the top of the frame, I'll use a trigger clamp to pull the handlebar metal into alignment with the frame's top bar. From the front of the frame, I'll secure the bottom of the handlebar first. I'll roll in a couple of T-nuts into the frame's bottom bar, hold a heavy-duty L-bracket in place, reposition the T-nuts with a hex wrench, and lightly thread a couple of M5 8mm screws. Since I'll need to massage the bracket into place, I'll leave the screws a little loose so I can easily slide it around as needed. Now I'll insert 2 more T-nuts into the handlebar, slide them into position with the wrench, and lightly thread 2 more M5 8mm screws. Once all 4 screws are started, I'll align the bracket to be as symmetrical as I can, and then tighten all 4 screws down completely. With these 4 screws secured, I'll remove the bar clamp at the bottom, the stop block, and the trigger clamp at the top. Still from the front of the frame, I'll repeat these steps to add an L bracket at the top of the handlebar, being as careful as I can to maintain symmetry throughout the endeavor. That wraps the installation of the first handlebar. Here's how it looks now fully attached to the frame. In early designs, I overly recessed the handles, sitting them too close to the radiator fans. When I'd grip the handles, my knuckles would scrape on the edges of the fans and not feel so great. By situating the handles further forward, I can easily grip them, and my knuckles and fingers remain clear of any frame material or components. Now I'll repeat these steps to attach the second handlebar on the other side of the frame. With both added, I can now remove the frame and carry it around if need be. While the handlebars are fairly heavy duty, I want to enhance their stability by tying them into the overall structure of the frame by adding a horizontal cross beam here. To that end, I'll cut a length of aluminum that is 20 1/16 of an inch long, and then roll in 4 T-nuts at these locations on the frame. Next, I'll roll in 4 T-nuts into the length of aluminum, with 2 paired together on each end. Once these are in place, I'll use 4 small silver brackets that I've ground the nubs off of one side to attach the bar to the frame using M5 8mm screws. Bear in mind that the side of the silver brackets that has the nubs should be oriented with the nubs inside the channel on the vertical sections of metal, and the flat side of the bracket against the metal being added. It's also important to make sure that this bar's edges are flush with the edges of the metal behind it. Once all 4 brackets have been tightened down, a single cross beam now connects the 2 handlebars into the frame's vertical supports. Another benefit of this arrangement is that each end of the horizontal support is open, which allows me the flexibility to continue to slide attachments in from either side. But first, let me switch gears and talk briefly about the reservoir I'll be using for this build. This is the Alphacool Core Distro Plate 240 with left side pump orientation and right side port orientation. The nomenclature is somewhat confusing, but this specific model is the Alphacool Core Distro Plate 240 Right 4VPP/D5. I really like its simplicity and build quality, and I've designed several elements of my wall mount frames around its specs and dimensions. On the back of the reservoir in each corner and up the middle are M3 threaded holes, though I only use the corner holes since those provide more than enough support. To attach the reservoir, I designed a series of 3D printed mounting arms. They each measure 24mm by 29mm by 24mm and have a 4mm thickness. The only variation is that one bracket has a small notch taken out of a corner to avoid the metal cover on the back of the distro plate. Each bracket has a 5.5mm hole for M5 screws to secure the bracket to the frame, and a 3.5mm hole for M3 screws to attach the reservoir to the bracket. To limit pump vibration transferring to the frame, I'm going to cut rubber strips to sit between the brackets and the surface of the reservoir. This is a 6" by 6" sheet of commercial neoprene that is 1/16 of an inch thick with a short A rating of 60/65. In total, I want to cut 8 pieces of rubber material. 4 pieces that measure 3/4 inch by 3/4 inch, and 4 pieces that measure 3/4 inch by 7/8 inch. I'll measure and mark the lines and cut with a pair of sharp scissors. With the pieces cut, I'll hold one of the 3/4 by 3/4 pieces against the inside back edge of the bracket, and then from the back, use a pencil to mark the M3 hole location on the rubber. Now I'll use a leather hole punch and hammer to cut the rubber material out from the hole location. With the rubber removed, I'll hold it up against the bracket to make sure there is a clean through hole. This process will be the same for all 4 pieces of rubber that need material removed for the M3 screw locations. Next, I'll attach a piece of heavy-duty double-sided tape on the appropriate side of each piece of rubber, position the rubber on the bracket, and press down firmly to secure it. As I go through this process, if I find any edges on the brackets that exhibit filament expansion where it touched the build plate, I'll use a flat needle file to very lightly take the edge down. With the back piece of rubber attached, I'll add the longer pieces of rubber along this edge, also using double-sided tape. Once all the brackets have their rubbers on, they look like this and are ready to attach to the reservoir. To mount the brackets, I'll use an M3 12mm screw and a number 6 SAE washer. I've laid the reservoir face down and will attach each of the brackets on their appropriate corner. Because of the unequal inset lengths Alphacool used on the reservoir's corners, each bracket will only align with one corner of the reservoir correctly. While screwing them down, I'm applying pressure with my fingers to ensure that the side of the bracket with rubber is firmly squeezed up against the acrylic. I'm also going to be very careful not to apply too much force when screwing these down, to avoid cracking the acrylic housing. Once all 4 brackets are attached, the reservoir looks like this, and is ready for the next step. To set the stage for what's next, I'm going to borrow what I consider to be Marvel's laziest storytelling device, the multiverse. As I'm sure is obvious, I've jumped to a different timeline where the water cooling loop is mostly complete and can safely pump water throughout the system. When the pump is turned on, the return chamber will collect any air that was pushed through the loop and behave as a self-pressurized column, leaving the fill chamber to do practically nothing. Swapping the ports has no positive effect, but thankfully from my testing, this problem can be rectified in a few different ways. Bear in mind that if there isn't any air in the loop to begin with, there wouldn't be a problem, but this is almost never going to be true for the initial filling at least. A trick I've used in the past to purge air trapped where it shouldn't be is to pick up the case and rotate it to guide the air to the bleed port. That just won't cut it here. Therefore, I'll explain the 2 methods I use to make this reservoir work beautifully in my wall-mounted builds. Personally, I'd prefer these 2 chambers exist as one, so the first of the 2 methods is to make that happen. I'll take the reservoir out to the shop and remove the 22 front plate screws. Once these screws have been removed, I'll lift the cover off and place it to the side, face down, on a clean paper towel. Next, I'll carefully remove the rubber sealing gaskets with the pointy end of a cleaning pick, being very careful not to puncture the rubber material. Now I'll cover the top plate and the gaskets with more paper towels to prevent acrylic shavings from getting all over the components and making the cleaning process before reassembly more difficult. To protect the reservoir, I'll apply masking tape over the entire surface and ball up some paper towels and stuff them in the channel openings so no acrylic shavings are flung deeper into the housing. I'll cover the channel openings with small pieces of masking tape as well. Now I'll orient the reservoir so the top is at the edge of the table. I'm no engineer, but if I had designed this unit, I would not have included this spine of acrylic here, which seems to do more harm than good. The folks at Alphacool are smart though, and I ain't, so they probably have a very good reason to have included it. But I'm going to cut part of it off to merge these 2 chambers into one. I'll use a Sharpie to mark the exact area where I'll remove the acrylic material. Ideally, this canal will be as high up on the reservoir as possible, without getting too close to the indented ridge that the sealing gaskets rest in. I'll place 4 1-inch washers in the bottom of each channel. These serve 2 purposes. The first is that if I slip with the Dremel, I won't mar the acrylic by putting gashes in it. The second purpose is to provide a depth gauge, so that once I am dremeling across the channel, I can be assured that I'm not going deeper than the washers allow. To make the cut, I'll use a Dremel and a 1/8 inch carbide carving bit. I'll slowly start cutting into the acrylic with small back and forth motions between the Sharpie lines. I'm looking to get as much of the material cut away as I can before I switch sides and come at it from another angle. Once I've cut the material down to the depth of the washers, I'll put a 1/4 inch sanding drum on the Dremel and now make slow back and forth passes on the acrylic to smooth out any imperfections. Once the shape is fully cut, I'll use 7000 grit sandpaper to smooth the edges. To sand the bottom of the canal, I'll make a U-shape with the sandpaper and slide it back and forth in the slot. I'm being careful to avoid scuffing up the surrounding acrylic during this process. With the cutting and sanding finished, I'll use the pick to grab the washers and start to clean the reservoir. After removing the tape, blasting the unit with distilled water, and doing some acrylic crumb management, the reservoir looks like this. It's very important to make sure that any leftover shavings are cleaned up prior to adding the gaskets back and tightening them down. To ensure the gasket tracks are clean, I'll use lint-free electronic swabs to trace the tracks and remove any debris. Here's how the newly cut canal between the two chambers looks. Now I'll put the gaskets back in place, align the top cover, and reinsert all 22 screws. I use the EK loop torque driver configured to 0.6 Nm to reinsert these screws. This is less than Alphacool's stated torque of 1.5 Nm, but this wrench has worked just fine many times over for this process. I'll visually inspect the gaskets under the acrylic cover to make sure they are compressed fully. And finally, here is the completed reservoir, all prettied up with its dance shoes on. With the reservoir completed, I'll reassemble the loop and tinkle some water in the fill port. Now that both chambers share a common pressurization, the water level rises and lowers in tandem. Once the end-to-end flow is established, I'll continue to add water until the reservoir is completely filled. Since both chambers now connect to the fill port, I can fill and purge from the same port. I especially like that I can now fill the reservoir completely to the top, minus about 3/16 of an inch. Happy with the results, I'll jump back to my original universe and continue the build. This was the first of two modifications I used to alleviate the reservoir problem. The second modification I'll explain later when we get to preparing the radiators. To construct the reservoir mounting apparatus, I'll cut 3 links of aluminum, 2 that are 10 1/2 inches long, and 1 that is 7 5/16 inches long. These pieces are joined at the top with 2 interior corner joints via M5 6mm cone-tipped set screws. The upper left corner has a 3/8 of an inch inset to ensure the space needed to insert the reservoir between the posts is perfect. From the open end of the newly added support bar, I'll insert 2 interior corner brackets into the T-slot. Now I'll slide them so that the middle of each bracket is located precisely at 11 1/2 inches and 17 1/8 inches from the left edge of the support bar. Once in position, I'll tighten the set screws to lock them in place. Next, I'll slide the reservoir mount legs down onto the posts of the brackets. With the mount in place, I'll tighten the set screws in the mount legs to secure it to the frame. On top of the mount, I'll add 3 silver brackets that have had the nubs ground off of both sides. In 1996, Jacob Dylan postulated that there was something better than in the middle. Well, he was wrong. So the first bracket will be placed in the middle of the T and L brackets. I'll roll in 3 T-nuts and lightly secure each bracket with an M5 8mm screw. Before cranking them down completely, I'll push the brackets on the outside edges to be firmly pressed against the T bracket and the L bracket. The reservoir mount is now attached to the frame. To mount the reservoir, I'll first roll in 2 T-nuts into the back channel of the reservoir mount on both sides. Then I'll set up a Hupar self-leveling laser level on a bookshelf and use an empty CD case to align the laser to the ports on the radiators. Since there will be overlapping tubing in this build, I'm going to need an offset on the horizontal axis to avoid the acrylic tubes running into each other. For now, I'm going to take 2 Barrow right-angle rotary fittings, connect them together like so, and then screw the angle into the top right position on the reservoir. Holding the reservoir in place, I'll align the mounting arms with the T-nuts and lightly thread an M5 8mm screw into each. It's a very tight fit between the reservoir mount aluminum with perhaps 1/32 of an inch of available play. This allows me to slide the reservoir up or down as needed to align with the laser level, and thus align with the radiator ports as well. Based on the position of the laser line, I'll gently slide the reservoir down until the line is centered on the Barrow fitting. Once it's perfectly aligned, I'll crank the M5 screws down, locking the reservoir into its forever home. The rubber pads we added effectively eliminate vibration and noise transmission to the frame, and, thanks to the floating design, no other parts of the reservoir come into contact with the frame. I'll now add additional offset posts to the left side of the frame. Here, I'll add a piece of aluminum that measures 12 inches long, and here I'll attach a piece that measures 9 9/16 of an inch long. I'll cut those lengths and then slide an interior corner bracket into the horizontal support channel in this orientation. Next, I'll set the 12-inch piece of aluminum down on the post and lightly thread the set screws until they start to grab the metal. On the top, I'll use 2 T-nuts and a silver corner bracket with the nub shaved off one side to lightly secure it in place. With these first 2 connection points established, I'll use a small machinist square to ensure the post is sitting as square as possible. Once it is square, I'll use a hex wrench to permanently tighten the set screws on the interior corner bracket, and then fully tighten the screws in the silver bracket at the top. Finally, I'll add another silver bracket on the opposite side of the bar at the top. In terms of placement, I want to ensure that the left edge of the metal is very well aligned to the edge of the opening in the motherboard tray where the EPS connectors pass through. I'll slide in another interior corner joint like so, and then sit the last vertical support down onto it. Positionally, I'll make sure the edge of this bar is perfectly in line with the vertical support behind it. Insert 2 T-nuts into the slots here, and then secure a 2.4 by 1 1/2 inch mending plate with M5 6mm screws in the top 2 holes. Once the top screws are secured, insert 2 more T-nuts below the mending plate, push them into place using a hex wrench, and secure them with M5 6mm screws. With the mending plate attached, I'll go back and ensure that the set screws at the bottom of this support are completely tightened down. Now I'm going to focus on tasks related to the water cooling loop. To set us off on the right foot, I want to ensure that the radiator mounts are centered in their respective spaces. From the back of the frame, I'll loosen the 4 screws holding the radiator mounts in place, 2 at the top and 2 at the bottom. From the front of the frame, I'll slide the mounts left to right until centered, and then retighten the 4 screws on the back of the frame. Since we've not utilized the radiators up to now, they are still as they come out of the box, and there are some prep steps I take to ready them for service. First, I'll remove the 4 screws holding each radiator to its mount, and remove it from the front of the frame. Next, I'll stand it upside down and remove the drain port screw. There is minimal space where the bottom of the radiator sits on top of the mount, so I'm going to attach a Barrow 15mm rotary offset adapter to give me some play in this area. To counteract a weakness of rotary fittings, I'm also going to use some hot glue to permanently secure this fitting while still allowing the rotary action to take place. Let me give a brief demonstration. This offset adapter will be tasked with rotating in and out of position to support loop draining as necessary. Unfortunately, the back and forth rotation of the fitting will cause the threads to come loose from the radiator. With the fitting completely threaded on, it takes about 1.5 rotations of the rotary neck to break the threads free. By applying a small bead of hot glue around the perimeter of the fitting, it will stay seated in the radiator while allowing me to take full advantage of its rotational characteristics without fear of what I like to call retributional moisturization. My glue sticks of choice are the Gorilla Glue 0.27-inch diameter mini glue sticks. For this task, I'll screw down the offset fitting as far as it will possibly go, and then apply hot glue around the edge of the radiator and up into the knurled diamond pattern of the fitting. Since there isn't much of a gap between the edge of the fitting and the radiator, glue won't seep down between the 2 surfaces in any meaningful way. In the future, if I want to remove or replace this fitting, I'll stand the radiator upright and use a heat gun to melt the glue. Once the glue is applied, I'll let it sit for 5 to 10 minutes to harden up. Now I can rotate the fitting to my heart's content and it won't pop out or pry free from the motion. Giggity gig. On the end of the rotary fitting, I'll attach an EK Quantum Torque drain valve fitting. This radiator is now prepared for the next step, so I'll set it to the side, remove the other radiator from the frame, and perform the same steps up to this point. With both radiators prepped, I'll perform an initial cleanse, so any lingering debris from the manufacturing process doesn't make its way into the loop. The hardware I use for this is as follows: a GE whole house water filter, a simple pond pump from Menards, string-wound water filters capable of filtering down to 5 microns, and some soft tube whips made out of Tygon S3 tubing that are outfitted with various quick disconnect fittings from Coolants. I'll slide a filter into the housing, ensure the bottom is fully seated on the alignment ring at the bottom, and then twist on the top until it's locked into place. I've moved out to the shop and have set up the system. The filtration process works like so. When I turn the pump on, distilled water will flow from the reservoir into the center of the Pentair filter, where it is then forced through the string-wound fibers, thus catching any debris present in the water, and then pushing the water out of the filter into the radiator, and then from the radiator back into the reservoir. First, I'll add some distilled water into the reservoir. Next, I'll turn the pump on and let the initial bit of water pass through the filter. I'll add more distilled water into the reservoir, and now the stream is running completely through the system. As air bubbles are purged, I'll add more water into the reservoir to top things off as needed. With everything flowing, I'll gently twist, tilt, and shake the radiator a few times throughout the process. It really doesn't take very long to perform this step, but just to be sure, I'll leave it sitting like this for about half an hour. After the time has passed, I'll start to disconnect the system in whatever manner makes the most sense to avoid getting wet. Now I'll hook up the other radiator and perform the same steps to cleanse it as well. Once both radiators have been processed, I'll disassemble the filter housing to see if there is any trapped debris. Sure enough, there is some kind of black flaking that has been captured in the filter. This is probably the most gunk I've captured out of these quantum surface radiators in a little while. Unfortunately, I don't know if some gunk came out of both radiators, or if it all came out of only one radiator. However, this activity highlights why, even when I'd prefer to skip this step, performing an initial cleanse is a pretty good idea. Since the radiators will stand vertically, the channels where water shoots down are more likely to trap air, which are the channels connected to the right port for both radiators in my setup. To address this, I'll unscrew the right stop plug on each radiator, and twist on a Barrow 15mm offset adapter. With both radiators flushed and the fittings attached, I'll slide them back into place on the frame, reattach the screws on the back, and test the bottom drain port rotation. On top of each radiator, I'll rotate the 15mm offset fitting so that it's pointing at the middle between the ports. Now I'll attach a 45-degree male to female rotary fitting, and finally top it off with a stop plug. As I'm filling the loop, this port becomes invaluable to quickly bleed trapped air in the downward flow channels of each radiator. This is the second modification I mentioned earlier that helps me prevent air buildup in the Alphacool reservoir. Between 3 fill and bleed ports, and the canal between the chambers on the reservoir, I've had no problems filling and maintaining this loop. Before I can proceed with water cooling, I need to decide where to place the primary NVMe drive so that the GPU doesn't interfere with its operation or maintenance. Like most things in life, this decision isn't as straightforward as it could be, so let me explain my thought process and the trade-offs considered. With the video card installed, the motherboard's cooling block is difficult to remove and appropriately reinstall over some of the NVMe slots due to the overlap from the GPU water block. The heatsink for the primary NVMe socket here is unaffected, so I can leave that where it is. To explain further, let me remove the GPU and the motherboard cooling block and discuss the characteristics of the M2 sockets themselves. Like most motherboards these days, the M2 socket interconnects are split with some connecting directly to the CPU and some going through the slower but still ludicrously fast Z790 chipset. It's always a good idea to study the block diagram in your motherboard manual to fully understand the layout of the communication paths for connected drives. For this motherboard, the M2C_CPU and M2A_CPU sockets are those that connect directly to the CPU, reinforced by the _CPU designator in the port name. The remainder connect through the chipset. The ideal scenario is to connect your M2 drive or drives directly to the CPU if possible, but ideal situations aren't, and as Columbo might say, there's just one more thing. As you can see from the block diagram for the Z790 Oros Master, if I connect a drive to the M2C socket, the GPU will automatically reduce speed to PCIe 4 8x operating mode, as opposed to 16x operating mode. This is a basic entry-level description of part of the problem, but it's enough to present the options I usually consider when doing a build. The first option is to put the drive in the M2C socket. The primary drawback is that it will force the GPU into 8x operating mode. Bear in mind that for the vast majority of use cases, there is almost no performance difference, especially in gaming, between PCIe 4 8x and 16x operating modes. The reality is that you're unlikely to even notice the difference if you're already achieving high frame rates in the hundreds. The positive benefits of putting the drive in this slot is that it is the fastest slot with the least amount of latency between the CPU. I can use the Gigabyte NVMe heatsink, which is nice and beefy, and the socket isn't blocked by the GPU. The second option is to put the drive in the M2A socket. The drawbacks are that it will be hidden completely under the edge of the GPU and is difficult to remove without first pulling the GPU completely out of the system. There is extremely minimal space under the edge of the GPU as well, so cooling the drive is more difficult. A solution I've used for this slot in the past is to use a riser cable, like this NVMe riser, to relocate the drive to another part of the frame. However, there are additional drawbacks to this tactic, which are separate from the current challenges being discussed. The positive benefit of using this slot is that the drive will still be connected straight to the CPU, but not force the GPU into 8x operating mode, though it would interface over the PCIe 4 bus as opposed to the PCIe 5 bus. The third option is to put the drive into one of the chipset sockets. The drawback to this is that there will be a latency increase since it isn't connected to the CPU directly. This latency increase won't be noticeable in the vast majority of use cases, though there are some scenarios that could exacerbate the effect. The positive benefits of using one of these sockets are that they are completely free from interfering with the graphics card, could support any size of custom NVMe cooler I wanted to put on them, don't require any additional hardware to make functional, and are still plenty fast for the use case I'm targeting. For clarity, the use case for this NVMe drive is to house the Windows operating system, contain the page file, and a few small applications to drive the function of the rest of the gaming ecosystem. In layman's terms, it's just going to hold Windows. Given that, I'm going to place the drive in the M2Q_SB socket. If I ever needed the drive connected straight to the CPU, I will still have access to the M2C socket and could move it there. However, in that case, the trade-off would be forcing the GPU into 8x operating mode. A picture is worth at least 57 words, so here's some examples of what the GPU link speed looks like with no NVMe drive installed, an NVMe in the M2C_CPU socket, and an NVMe in the M2Q_SB socket. So for now, I'll reinstall the GPU, set up the laser line, and now I'm ready to get back to water cooling. There's one piece of hardware I need to modify for the loop I'm installing. This is an OLED digital temp and flow meter from Barrow. Unfortunately, this is not a bidirectional flow meter, though I believe there is a newer model that is. There is a defined flow direction that must be followed for the meter to work. Let me demonstrate. Here we have a pump that is going to push water in through the right side port and out through the left side port. You can see when I turn the pump on, the meter reads the flow rate as expected. If I quickly switch the flow direction, with the water flowing in through the left port and out the right port, the meter now just sits on 0. The bad news is that some folks may not realize this, based on some of the Amazon review comments. The good news is that the flow direction can be changed with a screwdriver and 5 minutes of time. The right port is the default inlet port, and the left port is the default outlet port. In my case, I need the inlet port to be on the left, with the outlet port on the right. I'll remove these 4 screws on the right side of the unit, and once removed, I'll use this cleaning pick that has a hook on one end to grab onto an edge of the impeller tunnel palm and gently pull the sealed end plug out of the meter housing. Once the port is removed, the impeller will, usually, just fall out. By default, for a flow of right side in, left side out, the impeller sits like this. In my experience, more often than not, the buffer ring does not fall out on its own, so I'll vigorously shake it until it does come out. All we need to do is to flip the impeller orientation, insert it back into the meter housing, and then put the buffer ring in place. Finally, I'll close it back up by reinstalling the port and the 4 screws. I can test the installation by reassembling the test tubing, and now with the inlet port on the left, the flow meter reads the correct value. We can flip the tubes around with the inlet stream coming from the right, and now the value reads 0 once the pump is turned on. Jack ching bada bing. Now I can get back to the loop install. Let me make 5 quick points to address some basics. I've completed a number of hardline installs, and despite being comfortable heating and forming hardline tubing, I personally don't like the way that it looks. I much prefer seeing fittings at corners, despite the increased cost and introduction of additional points of failure, into the cooling system. I developed a simple tool that I use for most tube measurements. I'll show you how I use this in just a second. It used to bother me when I couldn't get all of the fittings for a loop in the same color. At this point in life, I don't care at all about the color of fittings. I'll use any color, anywhere, and still be able to sleep at night. For this build, I think I'll be able to get the job done between the black and silver fittings I have on hand. There's many different water cooling fittings out there. As a simple example, there's a little functional difference between these two configurations, despite one being a single fitting and the other being two fittings. If there's a specific reason I chose a certain fitting over another, I'll mention it as I go along. If I don't say anything about it, it probably just means that the fittings I used were the first ones I found that could do the job. As I proceed through this, when I say that I cut a section of pipe, that means I cut the pipe, reamed the inside edge of debris, chamfered the outside edge, and poured some distilled water into the pipe to remove any lingering flakes of acrylic. For hardline installations, I designed these very simple 3D printed clasps that fix two pieces of 12mm tube together at a perfect 90-degree angle. Once two sections of pipe are brought together, I use the 832 knurled thumb screws to tighten the clasp together via the serrated flange nut on the back side. This allows me to lay out the actual loop before cutting the pipe. I can't use this for every single connection point, especially those that are super close to components, but I probably use this for 70% of my measuring and cutting activities. Alrighty, let's install the system. Remove the plastic covers off the radiator ports. On the front left of the GPU, add a stop plug in the bottom port. On the front right of the GPU, add a stop plug in the top port. Cut a section of pipe 61mm long. Attach a Barrow 90-degree 12mm pipe to rotary male fitting. Attach another Barrow 90-degree 12mm pipe to rotary male fitting to the other end. Rotate the fittings to point in opposite directions, 180 degrees from each other. Twist the assembled piece onto the left side of the GPU. Attach a Barrow 90-degree 12mm pipe to rotary male fitting to the flow meter. Rotate the fitting on the GPU to point out. Twist on the flow meter assembly. Rotate and position the flow meter to face away from the front of the frame. Add a piece of masking tape for a bit of temporary support. Cut a section of pipe 232mm long. Cut another section of pipe 81.25mm long. On one end of the longer piece, attach a bits power 90-degree dual multi-link adapter. Insert the shorter piece of pipe into the other side of the bits power fitting. Unscrew the compression ring from the fitting on the flow meter. Slide the longer leg of the assembled section through the frame, slide on the compression ring, slide on the O-ring, twist into the fitting, and tighten down the compression ring. Add another piece of masking tape for temporary support. Screw together a Barrow 90-degree 12mm pipe to rotary male fitting to a bits power anti-twist rotary extender fitting. On the back of the frame, slide on the compression ring and then the O-ring for the Barrow fitting. Twist on the assembled section. Rotate the fittings up and toward the left port on the radiator. Twist the end of the rotary extender into the radiator port. Adjust the section of pipe to be as straight as possible. I designed these simple pipe clamps to aid in securing this section of the loop to the frame. It consists of a hanger and a clamping angle that is tapped with 832 left-hand twist threads. The two pieces don't actually exert compression on the tubing, but rather fit seamlessly around the pipe with no remaining wiggle room, which is then pinched together using an 832 half-inch knurled thumb screw. Remove the support tape on the longer section of pipe. Slide or roll in two T-nuts into the slot. Sit the compression angle on top of the pipe, align the support bracket to the T-nut, thread an M5 10mm screw, and add the thumb screw, but leave both loose. Remove the support tape from the flow meter and get it aligned perfectly to the frame. Once in the desired position, crank down the M5 screw first, and then tighten down the thumb screw the rest of the way. Now I'm going to add a second support bracket closer to the back to finish securing this section of pipe. So what was my definition of done here? The pipe obviously has been secured. There is equal distance between the pipe and the frame metal at these locations. There is equal distance between the top of the flow meter and the frame metal at these locations. and there's non-obtrusive access to the bezel plate screws. Everything looks Gucci sauce to me, so we'll call this section of the loop complete. On to the next. Cut a section of pipe 210 mm long. Attach an Uxel 20 mm male to female extender fitting to a Barrow 90-degree rotary adapter fitting. Attach another Barrow 90-degree rotary adapter fitting to the previously assembled fittings. Attach a Barrow 12 mm compression fitting. Slide the Barrow compression fitting's O-ring onto the 210 mm section of pipe, push the pipe into the newly assembled fittings, and screw on the compression ring. Align the assembled section to the top right port on the reservoir and twist into place. Attach a Barrow 90-degree female to female angled adapter fitting to the extension side of a Barrow 41 to 69 mm adjustable SLI fitting. Attach a Barrow 12 mm compression fitting. Slide the Barrow fitting's compression ring onto the other end of the 210 mm section of pipe, slide on the O-ring, then push the pipe into the newly assembled fittings, and screw down the compression ring. Rotate the assembled section up and toward the right port on the radiator. Twist the end of the SLI bridge onto the radiator, extend or contract the bridge to be in alignment with the arm coming off the reservoir, and tighten the collar on the SLI bridge. Let me briefly explain why I love SLI bridges so much. When I build a loop, I spend a decent bit of time thinking about how I can make future disassembly easier. By using SLI bridges on some of the primary components, when it comes time to take them apart, it's a great offset to the torsional and tension stress that results from trying to unscrew the fittings, which are now tightly coupled to the acrylic tubing via the rubber O-rings. This rotary fitting on the reservoir acts as a pivot point for this section of loop, and the SLI bridge reduces the torsional resistance of trying to dismantle the tubing and fittings without first giving them a space to flex into, and absorbs any outward force, rotational or tensional, into the overlapping shafts of the extendable fitting here. Here's an example. When I want to remove this section of loop, I'll undo the collar on the SLI bridge, pull the extension shaft away from the frame some amount, which creates a non-stressed buffer length for the fitting to be unscrewed, which also causes the reservoir fitting to rotate out, and then I just unscrew the main shaft of the bridge out of the radiator. No stress or hassle. With the piece attached between the reservoir and the radiator, the second section of loop is complete. On to the next. Cut a section of pipe 134 mm long. Slide the O-ring for a Barrow 12 mm compression fitting onto the pipe. Push the pipe into the fitting, and screw on the compression ring. Attach an Uxel 30 mm male to female extender fitting to a Barrow 90-degree rotary fitting. Slide the compression ring and O-ring for the Barrow fitting onto the pipe. Push the assembled section onto the pipe and tighten the compression ring. Twist the section onto the in port of the CPU water block. Flare the fitting out to one side and attach a Barrow 15 mm rotary offset fitting. Rotate the completed section clockwise around to the out port on the GPU. Massage the angle of the offset and tighten down. That completes the section of the loop between the GPU and the CPU. On to the next. Cut a section of pipe 134 mm long. Attach a Barrow 12 mm compression fitting. On the other end of the pipe, attach a Bits Power 90-degree dual multi-link adapter. Attach a Barrow 90-degree female-to-female angled fitting to the extension side of a Barrow 41 to 69 mm adjustable SLI fitting. Cut a section of pipe 128 mm long. Attach a Barrow 12 mm compression fitting. Attach a Barrow 15 mm rotary offset fitting to a Barrow 90-degree female-to-female angled fitting. Cut a section of pipe 188 mm long. Screw together a Barrow 90-degree 12 mm pipe to rotary male fitting to a Bits Power anti-twist rotary extender fitting. Attach a Barrow 12 mm compression fitting. Slide on the compression and O-rings for the Barrow 90-degree 12 mm pipe to rotary male fitting that was just assembled. Tighten down the compression ring. Screw the SLI bridge and 90-degree angled fitting into the out port of the CPU block. Tilt the fitting to the side and screw the 134 mm pipe length with the Bits Power multi-link fitting on the end. While holding the SLI bridge firm on the CPU, Twist the pipe up so the bits power fitting is aligned to the top through hole in the motherboard tray. From the back of the frame, push through the 128mm pipe length through the hole, add the bits power compression ring, then add the O-ring. Push the pipe into the bits power fitting and tighten down the compression ring. On the back of the frame, attach the Barrow 15mm rotary offset fitting. Turn on the laser level and align the 90-degree fitting and the Barrow offset to be in line with the radiator ports. Tilt the 90-degree fitting down slightly to make room for the next section of pipe. Screw the 188mm pipe into the 90-degree fitting. Rotate the pipe up and toward the right port on the radiator. Twist the end of the bits power anti-twist rotary extender fitting into the radiator. Since these little fittings have mighty resistance, I remove the fan to make it easier to twist into place. Massage the angle of the offset adapter to get that just right angle and dangle of the pipe. I printed this simple right angle support for the pipe just below the Barrow compression fitting. It has a 5.5mm through hole to support and allow slight wiggle for an M5 10mm screw. Roll in a T-nut below the fitting. Lightly thread an M5 10mm screw. Push the support up until it supports the bottom of the compression fitting. Tighten the screw down completely. One thing I try and achieve with this section of pipe that passes through the motherboard tray is to perfectly center the pipe in the through hole. I also try and do my best to maintain an equal distance between the pipe and this metal edge on the front of the frame. And that finishes up this section of the loop. On to the next. Cut a section of pipe 429mm long. Attach a Barrow 90-degree female-to-female angled fitting to the extension side of a Barrow 41-69mm adjustable SLI fitting. Attach a Barrow 12mm compression fitting to the 90-degree angled fitting. Slide on the Barrow fitting's O-ring and push the assembled section onto the pipe. Slide on the compression ring and tighten down. On the other end of the pipe, attach a Barrow 12mm compression fitting. Attach a Barrow 90-degree rotary fitting to another Barrow 90-degree rotary fitting. Attach an Uxel 20mm male-to-female extender fitting to a bits power anti-twist rotary extender fitting. Screw the two completed sections together. Screw the full assembly into the top left port on the reservoir, with the female port facing the left radiator. Twist the end of the 429mm section of pipe into the female end on the reservoir. Rotate the other end of the pipe up and toward the left port on the radiator. Screw the SLI bridge fitting into the port. This is a simple support bracket I designed and 3D printed. It has a 5.5mm hole on the mounting surface with two 45-degree gusset supports connecting to the main body. It also has a clamp portion which is tapped with right-hand 832 threads. This support will greatly enhance the rigidity along the run. Roll a T-nut into the slot of the aluminum behind the pipe. Lightly thread an M5 10mm screw, massage the support bracket into position, and tighten down fully. Position the clasp on the bottom of the pipe, thread the 832 1-inch thumb screw, and tighten down completely. That's the last section of the loop. Let's move on to some small tasks, primarily on the reservoir, to get this baby ready for water. For this build, I'll be using the Alphacool Apex VPP pump. It has a SATA connector for power and a PWM connection to control the pump flow rate. I'll use a hex wrench to take out the 4 screws around the pump mounting cover. The body of the reservoir already has an O-ring in the channel, so I don't need to change anything about that for the pump. I'll work the pump cover over the 2 wires and situate it in the pump cavity. Add the 4 screws back to the mounting cover and tighten into place. Once again, I'm using the 0.6 Nm torque driver from EK. Alphacool specifications state to use 1.5 Nm, but if it's not clear, I'm sensitive to how much force is used to attach things to acrylic. The dead souls of the housing bodies I've cracked over the years haunt me incessantly. Now I'll screw in stop plugs on both ports of the second connection bank on the reservoir. Cut a section of pipe 90mm long. On each end of the pipe, add a Barrow 90-degree 12mm pipe to rotary male fitting. Turn each fitting to point in the same direction relative to the pipe. Screw this port bridge on the reservoir to connect the top out port to the bottom in port on the top bank. Cut a section of pipe 55mm long. Attach a bits power black sparkle enhance multi-link fitting to the pipe. Screw an XSPC female-to-female rotary fitting onto the bits power fitting. Attach a Barrow 12mm compression fitting to the other end of the pipe. Add a bits power male to female 45-degree rotary fitting to the top middle port on the reservoir. Screw the Barrow fitting into the 45-degree angled fitting. And finally, top it off with a stop plug. Put a stop plug on a Barrow 90-degree rotary fitting and screw it into the bottom right port on the reservoir. This acts as an additional drain port to the 2 drain ports already present on the bottom of the radiators. For this build, I'll be using the Corsair Hydro X Performance Coolant. To make it easier to feed into the loop, I'll transfer it over to my trusty fill bottle, named Trusty. I typically perform loop testing for the first few hours on a separate power source than the computer's power supply. My go-to device is this raggedy old external 5¼ DVD drive bay that has a standard Molex connector that I can convert into whatever power plug I need, which in this case is a standard SATA power plug. I'll start to add the coolant into the reservoir until the capacity is full, and then turn the pump on to push the liquid through the system. This is a fairly large loop, so it will take a couple of repetitions to get the loop fully flowing. Once it is, I'll continue to add more fluid until the reservoir is completely full. Once the loop is completely full, I'll step around to the front of the frame to see what the meter has to say about the rate of flow. It's currently sitting at about 5.5 liters per minute, or roughly 330 liters per hour. Although the pump is very quiet running at full speed, with the headroom I have in the flow rate, I might try and massage the pump speed lower for a small reduction in the flow rate, but run even quieter. Or I may not. This computer is going to sit roughly 75 feet away from where it's used, so noise isn't particularly a factor, but we'll see what we see a little later on. And finally, here's the back of the loop, running full steam, happily pumping its life away. I'll leave it sitting like this overnight just to say I did my level best to try and get it to leak. If it doesn't leak, I'll move on with the build. We've covered a lot of ground, so I think that's going to do it for this video. It's worth saying, but I may never make another video again. But if I did, I'd probably install the front frame door, mount the SSD cooling fans, get the rest of the fans aligned correctly with the cables routed, and get a head start on some electrical wiring for the components. I hope you've enjoyed this demonstration. Thanks for watching, and out. You know, it would be a little anticlimactic to do all this water blocking and liquid pimping without at least some hint of the performance to come. Before I run any benchmarks, I am going to install the Gigabyte F14F BIOS update that was released on August 10th, 2024 to hopefully prevent damage to the CPU as a result of the widely reported voltage issues with Intel's 13th and 14th gen CPUs. Let me also say that my semi-extreme overclocking days are way behind me. I can't even spell overclocking anymore. My goal with delidding, water cooling, and using somewhat decent components is to achieve respectable performance while keeping the system as cool as possible, versus looking at temp and voltage reductions as gained headroom to push a little further. I can't say that I won't be doing any overclocking or load line tuning on this build, but I will likely end up running it pretty close to stock by the time I'm done. I'm pretty happy with these preliminary results, especially given no optimization, no settings tweaks, heck there aren't even drivers installed outside of the 4090 GPU driver. I've already achieved an elite uptime of nearly 10 minutes, and the news and interests application is running smoothly in the Windows tray. One thing I'm not too sure about is this weird Bench program that seems to be counting numbers on my screen. I better shut things off until I know it's set.